start. So just wait for 3 minutes. We will start at 8:05.
Okay, but it's not a syllabus currently.
So, what we will discuss today?
Yeah, in today's discussion, we will talk about linear maps and its matrix presentation. So last time we have already discussed, Sanity has already discussed about linear maps and injectivity, subjectivity of their injectivity and subjectivity. In today's discussion, we will see matrix presentation, how to present a linear transform by a matrix after fixing a basis, and then we will also see the kernel of linear transform.
Excuse me, sir.
Yes.
Last session notes, it's not uploaded in calendars. Where can we find it?
Notes are not available. What is not available?
In calendar, yeah. Last session was Monday. Monday instructor session. Notes is not uploaded in calendar.
Okay. Okay, I will say them. Okay.
Okay, sir.
Thanks for
Thank you, sir.
letting me know. I hope everyone can see the presentation. Is it visible to everyone?
Yes, sir.
No, sir.
So please wait, zoom it. Yes, sir. Now it is visible.
Okay. All right. Okay, so today's topic of discussion is about linear maps. So you guys have already uh, been introduced about the linear maps in the last session. In today's session, we will go and we will associate. So you already know about matrices, and this is a new This is a new terminology, new notion of linear transformation. So now we want to relate these two concepts together, and there is a way to do that. using basis. Okay, so basis you have already seen what basis are. Using basis, we can relate a matrix. We can represent a linear transform by a matrix. Okay, so in today's discussion, we will see that how to do it. All right, and then once that is done, then we will also talk about some important subspaces associated to a linear transform. Like there were some important subspaces associated to a matrix. What were those? Null space of a matrix, uh, right? Null space was one of the main subspace associated to a matrix. Okay. And then similarly, there is also a similar uh, notion for a linear transform. So that also we will look into this discussion. Okay, so let us, before we start, let us first recall what is linear transform is, or linear transformation is, or linear map. So you can call it whatever, however you like. So, so it is a function from a vector space V to W. So vector space V is called the domain because in terms of a function definition, and W is called the codomain. Okay, so a function is said to be a linear transform if it satisfies these two conditions. What are these two conditions? First condition is that it distributes among the addition of vectors, all right, for all vectors in V. And if you take a scalar multiple of a vector, then that the scalar comes out. Okay. These two properties together are called the linearity property of a linear transform. So whenever you need to check whether a given function is a linear transform or not, you need to verify these two. There is an equivalent notion for a map to be called a linear transform, which is highlighted in this box. Suppose F is a map from vector space V to vector space W, and it is a linear map or linear transformation. Then it is equivalent to have this property. Okay. So what we have done in this case, we have combined the first and second property together. Okay. And then if it satisfies these two properties, this property, if a function satisfies this property, then it is a linear map between two vector spaces. All right. Now it is those who are interested. It is a good exercise for you guys to check how to get. So let me write it as an exercise. Okay. So prove the other way around. So start with suppose you have a map F from a vector space V to W, satisfying this condition F V plus alpha V2 is equal to F V1 plus alpha V2, then F satisfies one and two. Okay. 1 and 2 of the definition. So those who are interested can do this exercise. Okay. So when you do this, you actually prove this equivalent statement. Okay, because one side of this equivalence statement is direct. If you assume that your function is a linear transform, then it will automatically give this relation. But the difficult part is the reverse. Okay. So when you start with this property, it will give you the both of the properties, okay, both of the linearity. That is what you do. See. Okay, so that is an exercise. If you want, you can try. Yeah. Now we have also studied about injectivity, surjectivity, and isomorphism of a vector space of a linear transformation in the last session. So if you start with a linear map F from V to W, it is called injective linear transformation if and only if the images of vectors, if the image of vector is equal to 0, then that vector has to be 0. Okay. So that is what the equivalent, one of the equivalent condition of being injected. So what does injective means? Injective basically means that injective means that each point in domain maps to a has a unique image in the photo. No two points in domain can map to the same image in photo. So which in the case of linear transformation becomes this condition. You just only need to check for 0. So 0 only has to have the unique image. You don't need to check for every other element. You just need to check that for 0, 0 has to have a unique image. No other element can map to 0 of photo, 0 vector of photo. Second thing that you guys have seen is the surjectivity. Okay. So a map is called surjective. Linear map is called surjective if image of F is the whole vector space, whole photo. So this definition is same as the set theoretic definition of a surjectivity. So there is nothing new to on that. Now an isomorphism is nothing but a bijection of a linear, fancy way to say a bijection in vector space terminology in terms of linear. So whenever a linear map is bijective, it is called an isomorphism. And it simply means that it is injective and surjective. All right, so this is the revision part. And okay, there is one more thing that we saw in the last session, that if you have a linear map from vector space V to W, where the domain and codomain has the same dimension, okay, then the isomorphism, then F is isomorphism is equivalent to F being injected, and it is equivalent to F being surjective. So you only need to know if the dimension of domain and codomain are same, then the map, if the map is injective, then it is an isomorphism. And if it is only a surjective map, then it is injective also, and then it is an isomorphism. So one of the either injectivity is sufficient or surjectivity is sufficient. You don't need to verify both of them. Verify one of the things sufficient. But that only happens when the dimension of codomain and domain are same. Okay. So what are we going to in today's discussion? So we are going to associate matrix to a linear transform. So let's okay. So first of all, let's start with this function. So this is a function from R2 to R2. Okay. And this is given in terms of a vector in the general form. Vector xy goes to 5x plus comma x plus 1. All right. Now, first of all, the question is this map a linear map? So my question to you guys is this map a linear map? Anyone? Is the question clear to all of you?
Yes, sir.
Okay. So the question is, you need to check whether this function is a linear map or not. How do we check linearity? You need to verify.
So the two
You can just work with this condition, right? So let's just work with this condition. So is it a linear map? Has anyone verified it whether it's a linear map or not? So we need to check the linearity condition, right? So let's check one by one. So first condition is f of so let's take two vectors. So how does the two vector will look like? It is an R2, so it is x1 comma y1 and x2 comma y. All right, this is how two vectors are in R2 as well. Okay. Right?
Yes, sir.
Okay. So now what we do, we first check the linearity condition. So the addition. So what we do, we take f x1 y1 plus x2 y2. Okay. And we need to prove this has to be equal to f of x1, f of x1 y1 plus f of x2 y. Okay. This is what we need to prove. So what is this right hand side? So what is left hand side? Left hand side. So what is left hand side?
So it will become 5 times x1 plus x1 plus 5
Yes, 5 times.
x1 y1.
No.
No, 5 times x1 plus x2.
So first do the addition.
Yes.
Do the addition first. What is the addition?
So x1 plus x2, y1 plus y2.
Exactly. Okay. Now you apply function. Now what is this function value?
So 5 times x1 plus x2,
Yes.
comma x1 plus x2 plus y1 plus y2.
All right. Now let's do the RHS. Okay. So what is RHS? This is your RHS.
So it
Now
will
what
be
is
5 times x1 plus y1.
x1 plus?
So comma and x1 plus y1.
Right. Right. And then?
And then so 5 times x2 and comma and x2 plus y2.
There. Now we need to do addition of these two values.
Yes, sir. So 5 times x1 plus x2.
Yes.
And comma and then x1 plus y1 plus x2 plus y2 or x1 x2 y1. Yes.
So do we get LHS equal to RHS?
Yes, sir.
Yes. So the first property says. Right. Now let's do the same thing for the second property. So for second property, let's take alpha to be a real number. Okay. And then let's verify the second property. What does the second property say?
So c times f c
Yeah.
times
C times. Okay, let's take C. C times x comma y.
x comma y.
Right. This is what we need to show.
Yes, sir.
Exactly. Now, what is the LHS?
So it will become cx and cy. So then
Yes. Cx, Cy. And then apply the function.
yes, sir. So 5 times
5C.
cx
And then
comma
Cx plus Cy. Right?
yes, sir.
And then RHS. For RHS, we have this C times f of xy. So we can directly apply f of xy first. So what is that? That is C times 5x x plus y. And now you need to multiply, scalar multiply.
Yes, sir.
You get 5cx, cx plus c. Again, the RHS is equal to RHS. So you will get that. So it is a linear map.
Yes,
Does
sir.
everyone agree with that?
Yes, sir.
Good. So this is a linear map. Now you can see this linear map. You can also think of this linear map by a matrix. What is that matrix? Let's see that. I am sorry, this place. Start it out. All right. So now, if I consider this matrix, okay, and I define my, if I define and I define a function, consider this matrix, and you define your function as a times xy. Okay. So what will you get if you multiply axy?
5x comma x plus y.
Yes. Now this is same as f of xy, isn't it? This is same as
Yes,
f of
sir.
x, right? So what does it say? So what you have done, you have represented. So you can think of a linear transform as a matrix multiplication also. And what exactly in the matrix multiplication you need to know? You need to know this matrix. How do we get this matrix? Okay. You only need to know this matrix. You don't need to know anything else. Knowing this matrix is sufficient. Okay. So how do we obtain this matrix? Now the question is, how do we get this matrix? Yes, we do get this matrix. How do we get this matrix? So for that, we use basis. Okay. You might see that I've written a standard basis of domain and codomain is matrix with respect to the standard basis of domain and codomain. What does this mean? So, in particular, what if you see what are the standard basis? What is the domain first of all? In this case,
So
what is the domain of the map?
the domain is R square.
Yes, R2 is the domain, right? So domain is R2. So domain is R2. What is the codomain?
Again R2.
R2.
Yes. What is the standard basis of R?
1001 of
Standard
R2.
basis 1, 0 and 0. Okay, so the same goes with the both of the domain. So in codomain and domain, we have the same basis because I'm working with the standard basis of domain and codomain. Okay, so we have the same basis in domain and codomain. All right. Now, yeah. Now what we do? Now we need to represent this matrix. So let's look at the image of domain. So I'm applying a function on domain. So I will look at the image of each basis. Okay, each basis vector under this matrix. Okay, so let's do that. So f of 1, 0
Excuse me,
and
sir.
f of
Your
zero.
screen is not clear, sir.
Oh, it's not clear.
Yes, sir. It's
Yeah.
blurry. Very.
Are you using standard basis in order to get the matrix?
Yes.
Okay, so you didn't just use the coefficients from the equation and make the matrix, right?
No, 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 no. So we will come to that. Just
Okay.
is it visible now? Is it visible? Is it any better?
Yeah, it's better.
It's quite better.
Yes.
All right. Okay. All right. Right. Okay. So now let's look at the images of standard basis under the linear transformation. So what is 1, 0? Where does the 1, 0 go?
So it will become 5, 1.
5, 1. Right. And where does the 0, 1 goes?
0, 1.
It goes to 0, 1. Right. Now So till this point, we have used the basis of domain. Okay, we have just looked at the images of basis of domain. Okay, of basis vector. Now the role of codomains basis comes. What is that role? So now we want to express each of this 5, 1 vector. Now this 5, 1 sits inside your codomain. All right. This sits inside your
Yes, sir.
codomain. So because 1, 0 and 0, 1 are also basis of codomain, so you can express any vector in codomain in terms of your basis, right? We know that. So now let's express 5, 1 and 0, 1 in terms of basis. So how do we express that? So it is a times 1, 0 plus b times 0, 1. Can anyone tell you what is a and b?
So 5 and 1.
Right. It is just 5 and 1. Simple. Uh, just 5 and 1. Right. Now similarly for 0, 1, if I want to express it in terms of 1, 0 and 0, 1, I will get 0 times 1, 0 and 1 times 0, 1. Right?
Yes, sir.
Now, if you look at these coefficients, so if you look at the coefficient of the first basis vector in terms of the basis vector of the codomain, this gives you a column 5, 1. It gives you a basically vector which is 5, 1, and it becomes the column of your matrix. Okay, so this is giving you a vector 5, 1, which becomes this. Similarly, if you notice here, you get 0, 1, and this gives you the second column. Okay.
Excuse me, sir.
Yes.
Sir, I did not understand this part. Can you please explain that again? Where you
Which part?
doing 1001 standard
1,
basis
0,
after taking?
1. There is no 100. I'm working at
I
0,
mean that the time where you take standard basis after that.
So I haven't done anything. I've just looked at the image because, okay, let me explain it again. Okay. So what I've done, I have started with domain and codomains standard basis. Okay. What are the standard bases? 1, 0 and 0, 1. Now, because the function is applied on the vectors on domain. So I'm looking at, I'm a curious mind, I'm looking at the, where does this basis vector of domain goes? 1, 0. So that goes to 5, 1. Okay, nothing much I've done. What is the other basis vector? The other basis vector 0, 1 goes to 0, 1. You just need to apply the function and then you just need to put these value and you will get these vectors. Okay, there is nothing fancy. Now, I have used the basis of domain till this point. I have not used the basis of codomain till in this point. Okay, so you can think of this as the step 1. All right, in the step 1, I have only used the basis of domain. Now, it's my duty to use the basis of codomain also. Okay. Now you notice because this function, you have used this function, so the value, the vector that I will get will lie in codomain. So 5, 1 lies in codomain. 0, 1 also lies in codomain. Okay. Now I know that any vector in a vector space can be uniquely written, can be uniquely expressed in terms of its basis. Okay. So that is what I'm doing. So I know I have a basis given for the codomain. I have expressed 5, 1 in terms of the basis. Oh, so if I do that, I will get 5 and 1 and 0 and 1 as the coefficient for the first vector. So remember, I'm keep on saying first basis vector and the second basis vector. So it must give you a sense that the order of the basis vector of domain must be important. So if you look at the first vector, first basis vectors in coefficients in terms of the codomain, you will get 5 and 1. It gives you, it corresponds to a vector, column vector 5, 1. And you notice that this vector is nothing but the column vector of your matrix A. Similarly, 0, 1 is the column vector of your matrix, second column of the matrix. Now, how do we say that it is the first column and second column? Okay. And whether 5 will come on top of 1. Okay, the 5 will be the first entry and the 1 will be the second entry, or 0 will be the first entry and the 1 will be the second entry. How do we say that? How do we decide that? That is where we need to fix an order. Okay. Now order where? Order on the basis. Okay. So that is where I need to fix an order in the basis. So I will say this is an ordered basis. What does it mean? It simply means that the vectors are given in an order. That means there is a first vector, there is a second vector, there is a third vector, there is a fourth vector, etc. Whatever, how many vectors are there depends on it. In this case, there are two vectors and there is order fixed. 1, 0 will be the first one, 0, 1 is the second. Okay. So if I respect in terms of 1, 0, so the vector of domain is 1, 0. That's the first vector. So the coefficients, its coefficient will correspond to the entries in the first column. Okay. This will correspond to the first column. First column. Okay. And because 0, 1 is the second vector in the ordered basis, so its entries will correspond to the second column. All right. Now that is fixed, that which one will give you the first column, which one will give you the second column. But in a column, which entry will be the first entry in the column or in the second entry of the column? Which entry will be the 5, whether 5 will come first or 1 will come first. How do we decide that? For that, you need to fix an order again on the basis of codomain. Okay. So that is where I fix an order on the basis of codomain. That 0, 1 is the basis of codomain, and the coefficient of 0, 1, 1, 0 will be the first entry in the column. Coefficient of 0, 1 will be the coefficient of the second entry of the column. Yes, Meg.
So we had because we have R2 in domain and codomain. So here
Yes.
we know that okay 1, 0 is first, and then in the codomain also 1, 0 is first. But then
Yes.
how are we fixing in the domain itself? How are we fixing the order?
No, that is given information to you. So when you say, whenever you have a matrix representation, that means there is an order basis fixed. There is an ordered basis given to you. Okay, in domain, and there is an ordered basis given to you in codomain. Okay, that is already given to you. That is already known. Otherwise, you cannot have a matrix representation. That is what I'm trying to say. Make sense?
Yes, sir.
Yes, Jatin.
Let's just say that the codomain is the dimension of codomain is R4. Okay.
Okay.
I mean R3. So you'll be using the basis
Okay.
of R3, the standard basis of R3. So at that point,
Yeah.
how are you supposed to find the linear combination with respect to the R2 basis?
No. Then your function will be so. Okay. So if your domain is R3, if your domain is R3,
Yeah.
sorry, if your codomain is R3 and your domain is R2, so you will be having a function like fy, which gives you a vector in R3.
Okay.
Do you see the point?
Yeah, I see the point. So you would be using
And then once you have a vector in R3, then you can express it in terms of the basis of R3. That is not a problem.
Okay, fine.
Right? Yes, Jatin.
No, I erased it by mistake.
Okay, fine. Understood. All right. So you understand, right? So we need to fix an order on the basis of domain, and we also need to fix an order on basis of codomain. Okay, that must be clear. So let me give you another example. Okay. Let's play a trick. So instead of taking the standard basis, okay. So whenever I say standard basis, that means the order is fixed. So instead of taking the standard basis, let me tweak up a little bit. Let me take the second vector of the standard basis first. Let me take this order of the standard basis. Let me take this order of the basis from standard basis. Okay. So then the matrix changes. Okay. The matrix changes, right? Because so I have taken this basis for domain only. So keep this in mind. I have taken this basis for domain, and I have kept the basis for domain to be the standard basis. Okay. So in column, the entries will be same. Okay. But the number of column will change. So yeah. So because now 101 is the first vector now. So its image, so whatever its image is in the column is in the codomain. Their coefficients, corresponding coefficient with respect to the codomain's basis, will give me the first column. Okay, so we already know from the previous explanation that F01 is 0, 1, and the express and this correspond to 0, 1 column 0, 1. Now we have kept the same basis for codomain, so the coefficient remain the same 0, 1, 0 and 1. So within the column, the arrangement is same, but the arrangement of column is changed because we have taken a different order of the basis in the domain. Okay, so you can play this game. Let's play this game. Is there any doubt?
Sir, so even if we change basis to anything, the elements in the matrix will remain the same, but
No.
order could be
Why do you
different.
think so? Why do you think so?
Okay, no, sir, it can change. It can, even the elements can change based on what basis we have taken. Yes, sir.
Yes, exactly. Right. So
Yes, sir.
let's take another basis. So let's take another basis to make things more clear or worse for you, depending on what's your status right now. So okay, so let's take this basis. Yes, Jitin, let me take this thing, and then I will discuss about it. So matrix with respect to, let's take a different basis. Of domain and the standard basis for codomain. Let's take the standard basis for codomain. All right. So what should we do first?
So first
We
we
just
should
look at
make the
image of each basis vector. So what is the first basis vector of domain?
So 5, 2.
No.
So the vector is 1, 1.
Yes, the vector is 1. The basis vector is 1. Now what is the image of this 1, 1? Look at the map definition. 5x, x plus y.
5,
So where does
2.
it map? 5, 2. Yes. What is the second vector of the basis of domain?
1, 0.
0, 1.
0, 1. Yes.
Okay.
What is the image of that?
0, 1.
0. Right. Now, domain basis part done. Now we need to work with the codomain basis. Okay. So now let's express each of that with respect to the standard. So we are working with the standard basis. So we know the coefficient, that is easy. it is 5 and 2, and then it is what? 0
0, 1,
and
0.
1. Right. Right. So now, can anyone tell you what will the matrix? How will the matrix look like?
So 5, 2 in the
5,
column.
2,
5, 2 in
5, 2,
column.
then 0, 1.
Right. It's 5, 2, and 0. Good. So you guys understand, right? Yes, Chetan, you had something to ask back then?
Yeah, sir. So the purpose of using basis over here is to, I mean, graphically, you're changing the projection of the am I, so basically change the projection of whatever you have on the graph, right?
Yeah, you can think of that because basis work as a coordinate, some reference system. Okay, if you look at the graphical sense, if you try to think of it in graphics, in a graph, on a graph, so what does the basis work? So the basis gives you a reference system. So what is the usual reference system that we work with? That x-axis and y-axis, which have 90-degree angle between them. They are nice one. They are the standard basis, right?
Yes.
Now you can have some other bases also. Those are not, as long as your vectors are independent, you can treat them as basis. If you have two vectors that are independent, that will be your basis in R2. So 1, 1 and 1, 0 also is a also form a basis. So you can take those two directions and you can express any other vector with respect to these two bases. So you will get a different coordinates.
Got it.
That is what basis does, right?
Yeah.
So so basis gives you a reference system. Now we are here. What do we have? We have two vector spaces. So two vector spaces means there can be two different reference systems, right?
Yes.
And now the domain has one reference system, codomain has another reference system. And now you are expressing now how to see that because the function is fixed, but if you change the reference system, the presentation in terms of matrix will change. That is what I'm saying. Because the
Understood.
reference system is changed, right?
Yeah.
So you cannot have the same representation. That has to be changed. And that is basically very beautifully encoded in this thing. That how does it change? Okay, there is a role of a basis of domain, and then there is a role of codomain, and it is completely determined by that coefficient that you get corresponding to the basis. So it basically all things boils down to some real numbers arranged in some nice fashion. Okay, that is what happens. So so this complicated linear transform simplifies in terms of a matrix. You can just represent this complicated looking linear transform by some matrix, knowing the basis of domain and basis of codomain, some ordered basis of domain and ordered basis of codomain. Okay, so this is what this thing does. Okay, all right. So now, so it looks like this point is clearly well understood to all of you. We can generalize this thing. Okay, there is no limitation that we can only work with R2 and R from R2 to R2. So there is no restriction like that, because whatever we have seen is what we can generalize that. So our domain can be some Rn, codomain can be some Rm. Okay, if you take your domain to be Rn, your codomain to be Rm, then the corresponding matrix will be of order m cross n.
M cross M.
Okay, right? And again, when you work with Rn, then you will have n many vectors. So for each vector, you will have n many vectors. Now you need to look at image of each basis vector in terms of the basis vector of codomain. Okay, and then you will get the column, the first column, the second column, the third column, and the nth column, because there are n bases. So you will get the nth column. Okay, and each column will have m many entries. Why m many entries? Because codomain has m bases. Okay, m bases. So this thing can be generalized. There is nothing that you cannot generalize. Everything can be generalized, whatever we have seen. So there is nothing uh, there is nothing special about R2 that we can do this. Okay, this all everything can be generalized. Okay, so what are the two key things that we have noticed here? The first thing is that the order of the basis of domain and codomain matters. Okay, if we change the order, we get a different value. The basis also matters. If you take a different basis, that means it changes. So what we will be working with? We will be working with ordered basis. That means you fix an order on the basis of that we are working with. Okay, so we call them the ordered basis, and then right, and the matrix that we obtain depends on the basis that we choose. Depends on the ordered basis that we choose. Okay, if you choose this basis, as you saw that the matrix was different. With this basis, the matrix was different. With this basis, the earlier basis, the matrix was different. So it depends on the basis, ordered basis, and you need to work with ordered basis. That's the one thing, and it depends on the ordered basis of domain and code. All right. These are the two key takeaways from this discussion. And the third takeaway is that you can generalize whatever we have discussed. You can generalize that to any vector space uh, that you have. Okay. All right. So let's do that. Let's do the generalization. Okay. Suppose you have a function from vector space V to W, and it is a linear map. Okay, where V is a vector space, V is a vector space, and W is a vector space. Okay, and also suppose dimension of V is n and dimension of W is m. So what does this mean? That there are n many ordered vectors in basis of V, and there are m many basis vector of W. Let's name them something. So we call the collection of all these bases of V to be beta, and the collection of bases of codomain, which is W, by gamma. Okay, and we denote the basis vector by Wi, and the basis vector for V by Vi. Okay. Now, what in order to write down the matrix, what is the first step? We start with the basis of domain, and we look at their images. Okay, so that is what we do. So first, we look at the image of the first vector. Okay, so let me do one thing. Let me do step by step. So much more. So we start with f of v1 because it is the first vector in the ordered basis. Okay, so this belongs to the W because it takes a vector, because function takes a vector in V and it gives you the vector in W. So it belongs to W. Now, because it is a vector in W, I can express fv1 as a linear combination of basis of W. So let's say these are the coefficient that you get. N1 sorry, M1. There are m many bases M1. All right. Now we do so. So these coefficients will correspond to a column, and what is their order? Their order is decided by the order of the basis of codomain. So the A11 will be the first entry, A21 is the second entry, and so on. AM1 is the third entry. And because we have this is the linear, we have started with the first vector from the ordered basis. So this is the first column. So first column. So it will give us the first column. So this is the first column. Okay, I can repeat this process. I can have V2. This will give me the second column up to Vn. This will give me the nth column. Okay, and let's say the nth column has this coefficient. Yeah, 1 comma 2 comma m comma. Now it is fine. Wm. All right. So this will give us the mth column. Sorry, this will give us the nth column. A1m, A2m, Am. All right. Now we can write down the matrix. So matrix A is, so first of all, this matrix is going to have how many columns?
mn columns.
N columns,
N columns and m rows.
rows.
So it is m cross n. First column is A11, A21 up to Am1. Second column would be A12, A22 up to Am2. And the last will be An1, A2, Am. So this is the matrix approach. Now what I will do, I will also write down in order to reference, in order to give me a reference that I work with beta and gamma. Okay. Beta and I will use this notation to say that I work with beta and gamma. What where beta was the order basis for B and gamma was the order basis for W. Okay. So for simplicity. So you guys have understood this idea. This is nothing but I've generalized this thing. For simplicity, you can also think of it as, you can write down this matrix A as the image of the first vector, not the image, the coefficient corresponding to the first vector in the first column, second vector in the second column, and nth vector in the nth column. This is also a shorthand notation. I have written down some way to remember this presentation, but it is good if you can just remember from the method. Either way. Okay. All good. So let beta is the order basis of B and gamma is the order basis of W. So what we have seen is that you give me any linear transformation. Okay. Here my V and W need not to be Rn or Rn. They can be some other vector spaces also. They can be some subspace of R2 or Rn or Rn. Okay. They can be anything. There is no limit to it, right? As long as you know the basis of those vector spaces, you can associate a matrix linear transformation. That is what this definition says. Okay. So in other words, as long as you know the ordered basis of domain and ordered basis of codomain, you can associate a matrix to a linear transformation. So working with a linear transformation is equivalent to working with a matrix, but matrix with respect to some ordered basis of domain and ordered basis of code. If you change the ordered basis, okay, then your matrix will change. So your matrix will change. So there will be a problem. So because what will be the problem? The entries will be different. Then you will have to. You cannot perform you cannot think of it as, if you want to get the image of out of that, and you will not get the same image. Okay, because you need to work with you need to fix a basis. You cannot change basis in between. You need to fix a basis at the very beginning, and once you fix the basis, then you can have this correspond that any linear transformation correspond to an M cross N matrix, and any M cross N matrix gives you a linear transformation. That we have already seen how you can define, given a matrix A, you can define a scalar multiplication A with B. This gives you the linear transformation. Okay, we can define a transformation like this. So you get a correspondence. Now, this correspondence is important in order to study the linear transformations. Okay. So what we have seen till this point is that any linear transformation can be represented by a matrix with respect to some ordered basis of domain and codomain. Okay. Now this thing will be important in order to this matrix, associated matrix will be important to study the linear transformation. So this completely includes the information of linear transformation. Okay, now let's look at an example, which is not the usual vector space that you guys are familiar with. It is not R3 or something. It is a different vector space. It's a subspace of R. Okay, but it is also a vector space in itself. So you think of this W, X, Y, Z, such that X plus Y plus Z is equal to 0. We define a map from W to R2 as this. Okay, so first, I want you guys to tell me a reason why this W is a subspace of R. I will give you some time. First, tell me why this W is a subspace of R.
Because there is a relation exist x plus y plus z equals 0, and we can write it in a linear combination of each other.
Not entirely correct, but at least some effort. Good. So this is your quiz one syllabus. This is not something that I'm asking which I have not covered. This quiz one. Quiz one just get over. So you need to be you should be able to give me quick answer.
So for subspace, we have to just two things. One is that the it should obey the plus and multiplication.
Yeah, so does it obey this? And why does it obey if it does?
Yes, sir, it does obey because even if I mean,
What is the addition here? What is this addition of two vectors in W?
0.
No, it's not 0.
Negative.
addition will be like
It's the negative of the third vector, which is whichever is remaining.
No.
so addition of two vectors will be just the addition of those coordinates
Right.
itself.
Right. Exactly. Because it is because we are proving subspace. Subspace of what? Of R3. Where does the subspace get its addition from? From the bigger space.
Yes, sir.
Right? What is the bigger space in this case?
So R3.
R3. Right? So the addition must come from R3. So if you take any two vectors from W, how will you define their addition? That addition will define as same as you define it in you have in R3 in case of R2. Okay. What the scalar multiplication?
Yes, sir, it will follow because it's coming from R3.
Right. So now the question is that is this a subspace? How do we know that it is a subspace? Is the
Yes,
vector
sir.
addition, is it closed under vector addition?
Yes,
Is
sir.
it closed under scalar multiplication? Okay, so yeah.
Yes, sir. It will be close
Okay,
because
that
if
is
we
true. It is closed. It is, yeah.
because if we multiply any vector, I mean any scalar c with xyz, so it is still a c time cx plus cy plus cz will still be 0 because c
Right,
is not 0. So x plus y plus z will
right,
be 0.
right. That is true. So in order to show that this is a subspace, you need to you take two vectors x1, y1, z1 and look at their sum. Okay, their sum will be x1, y1, x1 plus x2, y1 plus y2, z1 plus z2. Okay, z1 plus z2. Now, in order to be in W, what it needs to do what? It needs to satisfy this condition. So you check this condition. Does it satisfy this condition? Yes, it does. Why? Because x1, y1, z1, x2, y2, z2 also satisfy this condition. Simple as that. And same for the scalar multiplication. There is nothing fancy about it. Okay, so coming back to the topic. So this is a subspace of R3. Now we define a map from this. Now subspace in itself is a vector space. So you can treat that as a vector space itself. So you now define a map from W to R2 as this: xyz goes to y. Okay, this is clear. Now we need to find out the matrix representation. First, in the first case, with respect to the ordered basis this and the standard basis of R2. In the second case, I have the same basis for domain, but I have a different basis for codomain. Okay. So now, how do we say? How do we find them in case one? In case A, how should we start?
f of minus 1 comma 1 comma 0 is equals to
Yes,
1 comma 0.
1,0, right?
Then next
And
minus 1 comma 0 comma 1 is equals to 0 comma 1.
right. So basis of domain part done, right? Now
Then
let's
codomain.
work with the codomain part, right? And the codomain bases are standard basis,
Standard basis.
right? So you will get just 1
1
times
of
1
1
0
comma
and
0.
0 times
0
this
comma 1.
and 0
0
times
times
this
1 comma 0
and
1
1
times
times
0 comma 1.
right.
Yes,
So what is
so
the first
matrix will
column?
be 1 comma 1 and 0.
And the second column is 0
0 and
comma
1.
So this is your matrix, right? Good. What about second case? Part in B.
Then f of minus 1 1 and 0 is equals to 1 comma 0.
Yeah, the images are same,
Yes, sir.
right? Images are same. So, but we have a change of basis at the codomain level. So now we need to express 1 0
Then 1 of 0 comma 1.
as this, right? Now what are AB?
B is 1 and A is minus 1.
Yes. Does everyone agree with that? Do everyone agree?
Yes.
Sir, don't understand. I'm not able to understand this concept. How R3 is given and you are into R2. I'm little confused.
What is the confusion? Can you be very specific about it? Because I'm not going to repeat this again. Okay, when you know what you are confused about. So A is minus 1 and B is 0. Okay.
So B is 1.
Oh, sorry, B is 1. Right. Thanks. Right. Okay. So this, what is your first column? Then
minus 1, 1.
minus 1. Okay. What about the second column? What about the second vector? 0. So
1
0,
of
1 we
0,
need to
comma 1
express 1 of 0, 1
plus
and
0
0,
upon 1.
so second column is
1,
1,
0.
0. So what is the matrix in the
Minus 1,
second
1,
case? B
1,
case?
0.
Right. Okay. Good. So everyone understood, right? What we have done. So this part must be clear to everyone because we haven't done anything fancy, anything new here. And there is this part is already covered in uh, last 4 weeks. So I don't want to go through again why this is a subspace, why how what is the addition over here, what's the scalar multiplication. I don't want to go into that detail because that is already covered. You have already given a quiz over this, so this must be you must be comfortable with this. I will assume with this fact. Okay, I'm not going to entertain down on that. All right. So good. Good. Okay. So just give me a second. Yes. So now, so once this matrix presentation is clear to all of you, how do we work with that? Now we can look at some subspaces of associated with linear transformation. Okay. So for that, let us start with a function from R2 to R, which is defined as follows. It is a simple function. It just takes xy and it maps to x. Okay. Now consider this subset. Consider a subset K given by xy in R2 such that f of xy is equal to 0. Okay. Consider this subset. So first of all, it is a subset of R2. All right. Now what is R2? R2 is your domain. Okay. So K is a subset of your domain. Okay. Now why is this subset important? Because what it does, it is telling you what are the vectors in domain maps to a 0 vector in codomain. Okay. It tells you what are the vectors in domain maps to the 0 vector in codomain. That's why this subset is important. I will name this subset later, but let's find out what is this subset in this specific case. Can anyone tell me what is this subset in this case? This
Sir, 0 comma y could be anything belonging to R.
yes, good. 0 comma y, where y is anything in R. That is correct. Does everyone agree with this?
So please explain, sir.
So you need to find out K, set of all points in R2, whose image is the 0 vector. Now, what is the function given? Fx is equal to fxy is equal to x. Okay.
Okay, here. So if we
Yeah. For
substitute
this function,
f of
I'm
x
working with this function.
0.
Yeah.
Okay, sir.
Right. So this will be your subset. Right. So, and it is clearly a subset of R2. Now, question is this a subspace of R? Is K a subspace of R? Anyone?
Yes, sir, it is.
Yes, it is a subspace of R2. Right. So it is not just a subset of R2. It is a subspace of. Okay. In particular, moreover, K is a subspace of R. Okay. Now, what do we name this subspace? So this is a very special subspace. So why this subspace is important? So you can think of in terms of matrix. If you have worked with, you have seen matrix. Right? So in matrix, we also look at a similar type of vectors which you apply on which you apply your matrix. Then it gives you the zero vector. Okay, and we name that something. We call them null space. Right? Do you remember that? So we also name this subspace something because it also gives you some important properties. So we call this, for a linear transformation, we call this to be the kernel of F. Okay, kernel of F. In particular, we define the kernel as follows. Suppose V and W are vector spaces okay, and F is a linear map. F is a linear map. Then set of all vectors in domain which maps to zero vector of codomain is called the kernel of the function, kernel of the linear. Okay, and it is clearly a subset of domain, and in particular, it is a subspace of domain. Okay, how do you see that it is a subspace? So, in general, so let me shift this a bit up. Shift this there. Yes, Chetan.
So if T is injective, that would mean that kernel has only 0 as its element, right?
Nice observation. Yes.
I'm right.
Then
Right?
what does it further say? Can you say anything about the injectivity?
No.
Think about it. Kernel is a subspace. How to see them? So for subspace, so what is a kernel? Kernel is collection of all those vectors whose images are the zero vector. So what I need to check? I need to check V1 plus alpha V2 for V1, V2 in vector space in kernel of F. And C in R prove that V1 plus alpha V2 is also a kernel of F. So what you do is just apply what is the condition to be in kernel. The condition to be in kernel is that it needs to map to 0. Right. So just apply the function F V1 plus alpha V2. So what will you get? Now use the linearity. This is equal to this. So this is equal to the linearity. Now, first vector is 0 itself because V1 is in the kernel. Second vector, you apply scalar multiplication. You can be taken out. And that will be 0 again. Addition of 0 is equal to 2. You get this two, which implies that F V1 plus C V2 is in kernel of F, which implies that kernel of F is a subspace of V. Yes,
Sir,
Sambhavi.
can you explain this one more time, sir?
Which part is not clear? Can you-
This f uh, f of v1 plus c.
Which step?
Second step. How f of v1 is 0?
This.
Yes, sir.
What is f of v1 is in kernel, right? I
Yes, sir.
started v1 is in kernel.
Yeah.
So what is f v1? By the definition of kernel,
Like
it
image
should be
is
0.
0. Image is 0. Okay.
Yeah.
Okay.
Right? Make sense?
Yes, sir. Thank you, sir.
Okay, good. So kernel of f is also a subspace of V. That is clear. Okay, in generality also. Not just in this particular case, but in generality also, it is a subspace of the domain. Now let's look at some examples of kernel. So in each of the case, we need to find out the kernel. So let me do one thing. Let me just cut these first and then move on. Okay, so in the first case, you have a map defined to be like this. Let's call that O map. Okay, O from V to W, where O of V is equal to 0. Now, what is the kernel? Now, what is the kernel of O? So kernel of O is set of all vectors such that O of V is equal to 0. So, what does this say? What is the definition say? What is the definition? Is it equal to V itself?
Yes, sir. Because vector v could be anything.
Yes, exactly. Right? So the kernel of this map is V itself. We call such maps this map is called the 0 because it maps everything to 0. So map O is called T0. Okay. Now let's take the second example. Okay, what the second example? What is the kernel? Kernel is set of all vectors in V such that equal to 0. Right?
Excuse me, sir.
Yes.
Sir, can you again once tell what is ID written here? I got distracted while the class.
ID is the definition of this, the function, the symbol.
Okay.
Okay.
Should it be V? I mean the V itself.
Is it V?
No, it should be the zero vector, only zero vector.
Yes. Because IDV is what? It is just V. So it has to be 0 vector. V has to be 0 only in this case. All right. It is a 0 vector. And this map ID is called the identity. All right. Okay. Now let's look at this third example. Map R from Vn to Rn and V1 to Vn is an ordered basis of V. Okay, so you have a map from Vn to Rn, right? And you have already given a basis, ordered basis for the domain V1 to Vn. So suppose any vector V in V for any V in V. Now any vector V in V can be written as a linear combination of bases of V, right? And suppose their coordinates are AIs. Okay. So what you can do, you can associate. What you can do, you can write vector V as a coordinate A1. You can associate. You can think of that V has a coordinate A1 to A. Okay. With respect to this given ordered basis. Now, what is this map? This map basically takes the vector and it maps to this coordinate, which is an Rn minus with this coordinate A1 to A1, A2 up to An minus 1, and the last coordinate is 0. Okay. Last coordinate is 0. Now, what is the kernel of this map? Let's figure out. Kernel of R is set of all vectors in V such that R of V is a 0 vector, but in Rn. Now, what is a 0 vector in Rn? So, what is RV? RV is A1, A2 up to An minus 1, 0. And what is a 0 vector in Rn? It is 0, 0, 0 n many times. Now, you compare the coordinates. What will you get? A1 must be 0, A2 must be 0, up to An minus 1, all has to be 0. Right? Okay. But An can be anything. Right? There is no condition on it. An can be anything. Right? So, An can be any real number R. So, the kernel of R is basically, now these are the coefficients. AIs are the coefficients with respect to the basis VI. So you plug these coefficients back into VI. So what will you get? Because all the coefficients are 0 other than the An and coefficient. So you will get it to be An Vn, where An is a real number. Okay, this is the kernel of. So it is a span by one vector. So it is what? It is nothing but the span of Vn in V. Okay. What is the dimension of this kernel? One dimension. All right. Okay, let's skip this one for now, and let's discuss the other the upcoming things. Okay, so what you have noticed here is that we have figured out the kernel of a vector space. We have explicitly figured out the kernel of the vector space in these three examples. Okay, in this case it was 0 subspace, in this case it was whole subspace, and in the third case it turned out to be just the span of one line. Okay, one dimensional subspace of. Okay, so there is a simpler way to find out the kernel of a vector of a transformation. Okay, so with respect to using the null spaces. Okay, and for that we will use the representations of matrix representation of a linear transformation. So suppose you have a linear transformation f from V to W, and you have ordered basis V1 to Vn of domain and ordered basis W1 to Wn of W. Then the kernel of f is nothing but the null space of f. Why? Because What is kernel of f? So kernel of f is set of all vectors in V such that TV is equal to 0. Right? Now f. So in our case, okay, I'm working with f. F is equal to 0. Now, in our case, we have associated a matrix AF. Okay. So if and how does the AF work? So for AF, you need to have some coordinate presentation like we had in the case above. So you can, with respect to basis, ordered basis, you can have a coordinate presentation. Okay. For each vector. And you can multiply that. So you can take vector in V. And what you can do, you can have basis, you can have this matrix representation, and then you can have basis V with respect to beta expressed. So what does this mean? This means simply that if V can be expressed as AI Vi, then this is nothing but A1 up to AI. Okay, is equal to 0. This is equal to 0. So finding a vector here in this kernel is same as finding the coordinate presentation of that finding the coordinate presentation with respect to the matrix. Okay. Once you get the coordinate presentation, then you can recover the vector also. Okay, by just multiplying it with the basis. Okay. So these two things are equivalent. Finding a solving this is same as solving for kernel. Okay. And we already know how to solve this. How? This is nothing but a null space. This is nothing but a null space of matrix A. Okay. This is nothing but the null space of matrix AF. AF means the matrix associated with F with respect to beta basis of domain and gamma basis of domain. That is what this notation says. There is nothing much about it. Don't get bothered by this notation. Okay. So the kernel of function is same as finding out the null space of this matrix. We have already seen how to represent a linear transformation via matrix. We have already seen that. And now we will use that matrix presentation to find out the kernel of the linear transformation. Okay. And we already know how to calculate a null space of a matrix. Can anyone recall? There is something to do with the row estimate.
Should get into RREF form and then
Yes.
equate it into
Yes.
independent variables with respect to dependent variables.
Yeah, then we write dependent variables in terms of the independent variable. That's how we get.
Yeah.
Good. So you guys remember, right? So that will give us the kernel. So what we have done till now, we have first of all reduced the problem of working with linear transformation to matrix. Okay. And now we are using one of the application of that. What's the application? That kernel, which is one of the important subspace of a linear transformation, is nothing but the null space of a representative matrix. Okay. So this is how we have translated our problem into a known problem. Okay. All right. So before we go into finding out a null space, this is something that we have already seen. So what is a F is a injective linear transformation. That means it is equivalent to, this is same as that f of v, if f of v is 0, then v has to be 0, right? Which nothing but means that kernel of a function is 0. Okay. So I'm using two equivalent definitions. So this is first equivalent definition that we have seen in the last session. And this is the definition of kernel that you have just seen. Now, these two definitions gives you this particular equivalent condition that function linear map is injective if and only if your kernel is a zero subspace. Okay. And we have already seen that kernel of F is nothing but the null space of the represented matrix. So when we say when can we say our function is linear transformation is injective, where your null space of the represented matrix is 0. And when do we say that the matrix null space of the matrix is trivial? When it has full rank, right? When the matrix has full rank. Okay. There is no independent variable there. Right. So in other words, because we have already associated kernel equal to null space, the dimension of the kernel is nothing but the nullity of the representative matrix. These things are just one by one correspond. There is nothing much we are going into, but it is realization. Once we realize that kernel is nothing but the null space of a matrix, then we get this for free. Okay. Okay. Just give me a second. sorry guys for the in between disturbance. Usually we don't have that. I'm sorry for that. Okay, let's come back to the topic of discussion. So till now we have seen that finding kernel is same as finding the null space of the represented matrix. Now let's see that in application. So let's work out this example first. A simple example, then we will do the harder example, and then we can try to formulate a algorithmic way to do that. Okay. So let's work out with this example. So you have a standard basis given on the domain. So let me write it more precisely. Hello. So suppose domain has standard basis. Codomain also has standard basis. So what is the domain? Domain basis is 100. Like what is the codomain basis? Codomain basis is anyone?
Sir, the same. Oh, sorry. Okay, 10. Yes, sir.
Yeah. So I think Jitin asked me that can we have a map from R2 to R3, something like that. Now we have a map. So you see, right? Because now you have the image. The image also is in R3, so it has to have a vector in R3. Now you can express any vector with respect to the standard basis. Right? So I think that now is clear to you. So now what's the first step? To have we need to first write down the presentation, right? Matrix presentation. So how do we do that? So first step is to write down the presentation, matrix presentation. So which basis we need to start?
1, 0.
1, 0. Right. One image of 1, 0 is 1, 2,
2,
3.
3.
And image of 0, 1 is right. So this will correspond to the first column. This will correspond to the second column. I'm not writing that again. These two images are in the codomain, so we can express that with respect to the basis of codomain. So it will give us 1, 0, 0, 2, 0, 0, and 3, 0, 0, 1. And we have 0 times 1, 0, 0, 0 times 0, 1, 0, and 0 times 0, 0, 1. All right. Now, what is the matrix?
So column 1, 2, 3.
1, 2, 3 and 0, 0, 0.
Right. Good. So it is a 3 cross 2 matrix. Right. Now, we need to find out the kernel of this. It is same as finding out the null space of this matrix. Okay. So how to find out null space of this matrix? What we need to do?
RREF form will do. And
Yes. So can you tell me the operations also? It is simple.
the 2 times R1 is subtracted from
R2 minus 2R1 and R3 minus 3R1 will give you 1, 0, 0, 0, 0, 0. So this is an RREF form. What is the nullity of this? Or how many dependent variables, independent variables?
so one dependent, one independent variable is there.
Yes. So what is the nullity?
Nullity is 1.
Nullity
2.
is 1.
Oh, my bad.
Yeah. So nullity is 1. Right. Now, yeah. Now write down the matrix. Okay. So now write down find out the basis of that. So it is 1, 0, 0, 0, 0, 0. And we have we have x, y. Now what we will get? We will get x and we need to equate it to 0, 0, 0, right? So what will we get? We will get x 0, 0 to 0, 0. So this implies that x is 0, but there is no condition on y. So y can vary in R. So my kernel is x. My kernel is 0, comma y in R2, where y is my kernel is 0, comma y, where y is in. This is my kernel of f. Okay. Okay. Now let's do this question. So in the previous question, we had the standard basis. That's why there was no problem. Okay. Now let's see what will you get, because what I'm trying to say here is that the basis that you will obtain, sorry, so the vector that you will obtain, it is y. Okay. So now let's do one more thing. Let's find out the basis also. So can anyone tell me the basis of this? You can take y common
0, 1.
and 0, 1. Right. So it is the span of 0, 1 vector. So 0, 1 is the basis. Now this 0, 1, 0, 1 is actually coordinate. 0, 1 correspond to the coordinates with respect to the ordered basis of this. So that is fine. Right. That is the same thing. But let me
Sir?
Yeah.
So can you repeat just the last statement you were saying, that the 0,
Yeah,
1? Yeah.
Yeah. So 0, 1. What is 0, 1? 0, 1 correspond to the coordinates with respect to the basis of domain. Okay. So if there were some other basis, let's say 1, 1 or 1, 0, something like this, then you need to multiply that with each coordinate wise, and then you will get the basis, and then you will get some vector with respect to the standard basis of R. But in this case, it is already given to be standard, so we don't need to do that. That is what I was.
Okay, sir. Okay, sir.
Yeah. Right. So right. So now let's work with this example. So let me cut this part. Okay. Suppose we have a standard basis for R2, okay, which is this, and we need to find out basis for W. Okay, first of all, I'm not going to ask you again, but I want you to be comfortable with that this W is a subspace of R. Okay. All right. So now how to find out the basis of that? So what we will do, we can, this is x plus y plus 2z equal to 0. I have explained this in one of the revision session, I remember. So can anyone tell me how do we find out the basis from this?
Yes, sir. And then x equal to minus y minus 2z.
Yes.
And then we can substitute this in the in our coordinates.
Yes. And then I mentioned one method. You need to take, because there are two variables.
Y equal to 1, z.
One, right. So this will give you the first vector, -1, 1, 0. What about the second vector?
So
For second vector, you take y0 and z1, right? So -2, 0, 1, right? So this will be the basis. So the basis is of W is -1, 1, 0 and -2, 0, 1. All right. So we work with this basis of W and the standard basis form. Okay. Now let's define your map T from R3 to R2. Sorry, not W to R2. Take X, Y, Z, T, X, Y, Z. Okay, let's take, instead of taking it to R2, let me take it to R3. Then we can have basis 1, 0. And then you have the standard basis form. So that's not one to mention. Okay. Now this goes to what? This goes to X, Y, Z as it is. Okay, this is my map. T from W to R3 defined as this. Now we need to find out the kernel of this map. So what is the exercise? First, we need to start with the basis, and then basis of the domain, and then the basis of in terms, and then basis of codomain. So what is the basis of domain?
So -1, 1, 0.
Right. What is the image of this? It is
-1, 1, 0.
And basis of codomain is again second factor of basis is this. We will get this. Now we need to use basis of codomain. So the copes, because we are working with the standard basis of R3, we don't need to think much. So this will be the column itself, right? We will get this as the column itself. So what is the matrix?
So column wise, -1, 1, 0 and -2, 0, 1.
Good. All right. This is your matrix. Now we need to find out the null space of this matrix. So null space of A -1, -2, 1, 0, 1. Okay, what do we need to apply now?
R1 plus R2.
R1 plus R2. This will give you 0, -2, 1, 0, 0, 1.
Then interchange R2 and R1.
Okay, we can do that later. Okay.
Okay, then R1 plus 2 R3.
Right. and then now you can interchange
R1 at the last row.
twice. So you get 0, 1, 1, 0, 0, 0. You need to do one interchange, R1 with R2. Okay. So right now, what is the nullity of this space?
So nullity is 2.
Nullity is 2.
Why? Why nullity is 2? How
So
many
nullity
independent
is 0,
variables?
no? So 0.
Yes, it is 0. There is no independent.
Both are
variable.
dependent.
Both variables are dependent. Nullity is 0.
Yes.
How many dependent variables are there? 2.
The two
How many variables are there total? 2. So
Yeah.
there is no independent variable. Nullity is 0. So what is the kernel? What is the null space of this matrix?
So then 0 only.
Null space is 0. That means kernel is also
0.
right. Right? Make sense?
Yeah.
Good. Okay, I wanted to do one example where I have some coordinates so that I can express that coordinates. I can tell you what it is. So let me start tweaking this. So let's take this. So I'm working with the same spaces. Let's take a map R from W to R2. Okay, and it is defined as X, Y, Z. R goes to X, 0, 0. All right. Now let's see this. So R of what were the bases? -1, 1, 0. -1, 1, 0. And R of -2, 0, 1. Now where does this go? This goes to -1, 0, 0. And where does this go? This goes to -2, 0. Right. Again, I have, sorry, with R3, not R. Now again, because we have the standard basis on R3, these will correspond to the columns. So the matrix will be -1, 0, 0, -2, 0. Now, what is the nullity in this case? Now I can perform one operation. There is one row operation that I need to do. R1 minus R1. So I will get 1, 2, 0, 0, 0. So nullity. So there is one dependent, one independent variable. Nullity is 1, right? So in particular, now I will solve this equation. This xy is equal to 0, 0, 0, 1, right? So we'll get x plus 2y 0 and 0 equal to 0, 0, 0, 0, which implies that x plus 2y is 0, which implies that x is equal to -2. Okay, so null space is x equal to -2. But okay, so let me write that down. -2y y, where y varies in R. This is the null space of A. That means it is the span of what is the basis? Can anyone tell me what is the basis? -2, 1. Right? Span of -2, 1. Now this vector, the vector that you obtained here, this is a coordinates. This is the coordinates with respect to the domain basis. Okay, with respect to the basis of domain. Now, what were the basis of domain? This is the basis of domain, and you have obtained the coordinates. So if you want to find out the actual vector that spans the null space, okay, so you see the contrast, right? You are here, you are getting two, you are getting a vector in R2, but your domain has vectors in R3. It doesn't, it's a mismatch. No, it's not a mismatch. What you are getting is the coordinates, basically the coefficients you are getting, and you can recover the vector by taking this coefficient and multiplying with the first basis vector and the second basis vector. So what I'm saying is, so the kernel of f is -2 times the first basis, which is -1 0 1 0, and 1 times the second basis, which was -2 0. Right? Kernel is nothing but the span of this vector. So now, what is this vector? This vector is -2 times this. We'll get -2 -2 0 plus -2 0 1, right? And if you add them, what will you get? You will get span 0 -2 1. So the kernel is of this. So you get whatever after solving the null space, you get coordinates. You need to remember this. Whatever you get is coordinate, and then to recover the basis, in order to recover the vector, you need to take that coordinate and multiply with the basis of the domain. Okay, appropriate basis of the domain, and then you will get the actual vector from the subspace. That is what I want to discuss. So now, what is the algorithm that you see here? So first, we need to find out the matrix, okay, that represents your linear transformation. Then you convert your matrix, then you find out the null space of the matrix. Okay. At the end, you will get the null space, this basis for null space. At the end, you will get basis of null space. Those bases are not the basis of your original, are not the basis of your kernel of the linear transformation. Those are the coordinates. Okay. Now you need to work with those coordinates and express and find out the vector for each coordinate, for each vector in the null space. For each basis vector of the null space, you will get one vector, one basis vector for the kernel of it. Okay, so this is the algorithm. So algorithm, if I write down, so first step is to find matrix representation of F with respect to the order basis of domain and domain. Second is matrix representation A. Okay. So your T is a map from V to W. Second step, find null space of A. Find basis of null space. Okay, suppose you will get some basis A1, A1 up to some AN and AN and A1 1 A to 1 A to 1 up to A N 1. Something like this, you get something like this. Then third step is find basis for kernel. by taking each vi to be ai a1 ai1. Okay, let me take different equation. Ui to be oh uj for j varying in 1 to n and I varying in 1 to n. So you will get u1 up to un. Anyway, this is very general thing. You will not get this general thing. You will get just one vector, one coordinate, or two coordinates in null space, and then you can express corresponding two vectors. Okay. Okay, so we stop today's discussion at this point. In the next session, which is next time, exactly, you can check the calendar. Lavanya will talk about the range of a linear transformation and then some calculation. Okay, good night, everyone. Thank you for your attention.
Thank you, sir. Thank you for your time.
Thank you, sir.